Assalamu alaikum. Today I shall be talking of solid state lighting and the fascinating world of light emitting diodes and laser diodes. So, solid state lighting is actually nothing different than what we see these days. We have light emitting diodes, we have AMOLEDs, mobile screens, we have laser diodes in our computers, laptops, various LED indicators. So today we shall be uh, briefly talking about what these devices are and how they have influenced and they have been influencing our world. So kindly next. Briefly about me, this is our body of work. Some very exciting people you can see in the image below. And because of these exciting people, we have been able to gather some numbers, which you can see on the right side of the poster, number of publications, research grants, international reviewership. Um, and most of them, a lot of them are well placed, fully funded PhD scholarships in different parts of the world. That's me again. Recently, I've been listed on the Photonics 100 list. If you know time 100 list, if you know post 30 under 30, so this is a similar kind of list which acknowledges different uh, talents from different parts of the world. So you can see from USA to Pakistan, and I'm the only one representing Pakistan on this list. So I think some honor, some humble honor for Pakistan. Um, what I shall be talking of in this session would be what light emitting diodes and laser diodes are, some applications, of course, and then how 3, 5 compounds, semiconductors, anybody who is somewhat familiar with semiconductors would know group 3 elements, group 5 elements, and the combination of the two kind of elements would give us light emitting characteristics. So this is the images that you see. This is the evolution of light from candles to the incandescent to the energy savers that we typically call, which are CFLs actually, and then the modern day LEDs that we buy from stores these days, and all these what we see is now LEDs. How LEDs and laser diodes actually work? So we have one P side, we have one N side, and the electrons from N side and holes from P side recombine in the active layer, in the active region. When they recombine, they emit light. And this is the light emission process, whether we talk of sun, whether we talk of bulbs, whether we talk of any light emission. Whenever this kind of mechanism works, electrons and holes recombine, we have light emission. And why laser diodes and LEDs have taken over the world over the years, over the recent 40, 50 years, because of their longer lifespan, less heating. They don't use any mercury, any hazardous materials. So if you move further next, Sana, this is the basic difference between LEDs and laser diodes. Basic difference in the physics of light emitting diodes and laser diodes. So we have a photon coming in the first top figure, figure A. It excites electron from energy level 1 and it takes it to energy level 2. When we talk of light emitting diodes, there's this process called spontaneous emission. The electron which has gone up in the E2 has to come back, whether it comes back in a spontaneous way, whether it comes back after some stimulation. The difference lies between the two processes. So if it comes back spontaneously, we call the emission as we categorize the emission as light emitting diodes. If we have to stimulate the excited electron in the E2 to come back because of that external stimulant, the kind of light that is emitted is categorized as laser light, which fits in the definition of laser diodes. This these are few logos of various international societies that propagate, promote, um, um, and explore the world of lighting. World of lighting starts from the light emission to the light absorption, so light emitting diodes, laser diodes, photodiodes. So these are a few world leading societies. We have OSA in GIK as well, which is now known as Optica. We have Spire in GIK. IEEE Photonic Society is another leading world renowned society that celebrates lighting. And these are few reading magazines. The last magazine, Electro Optics, is the magazine that has compiled the Photonics 100 list actually. And there, as I just mentioned a few months ago, I was listed in the Photonics 100. So this is, I just mentioned, similar to Forbes 30 under 30 or Time 100. So Time magazine, Forbes magazine. Moving further, sustainable development goals. So the world is quickly adopting these goals. So what has it? What kind of relation it has with the lighting? So the 17 sustainable development goals, each has its own color, and all those colors are embodied in the logo of International Day of Light, which is celebrated on 16th May of every year. So this shows how lighting contributes. First, we know without light there is no life. If there is no sun, there is no photosynthesis, there is no plants, and if there are no plants, which means there is no oxygen. So light is life. Um, in fact, there's this interesting verse from Bible which says, um, "Let there be light," which is referred to, which is one of the verses of the Bible, which again shows there light was one of the starting moments of the universe. These are some few leading luminaries, pioneers of the world of lighting. So we have Losev, a Russian guy. He observed light emission, but he could not conceive it the way we today know as light emitting diodes. This guy, Holoniak, is father of light emitting diodes. He passed away recently. He's also the first guy who developed visible laser diode Holoniak, and that guy Robert Hall is the first guy who came up with diode lasers. So there have been lasers in other forms, ruby laser, gas laser, etc., etc. But laser diodes have been is actually the work on laser diode is highly affiliated with these guys. And then Nobel Prize in Physics 2014. These three guys that you can see on your screen, they won Nobel Prize for fabricating, producing efficient blue light emitting diodes. Moving further, so these are the applications that we just mentioned briefly already. We have lighting all around us, mobile phones, devices, automobiles, and so on and so forth. This work actually inspired us. I've had this work, I've had this image in my mind for some time, for quite some time actually. And then that led me to produce this work with my amazing students, perspective on light fidelity. We are aware of light Wi-Fi. So light fidelity is actually Li-Fi, and how we can use the light that is already available around us to propagate data, to use it as a source of data communication. Moving further, we have display screens. This screen actually also that we are using to display our work is LED screen. Recently, Jiki bought this LED wall that you all might have seen already. You might have seen some exciting cricket matches as well. Moving further, you might have seen these kind of boards these days on roadsides, which display advertisements of various forms for various agencies, and this is also LED based. Further, um, this thing actually, the use of UV light to kill to kill coronaviruses. There are different kinds of coronaviruses. One is COVID-19 actually. So this actually triggered us to explore the UV spectrum of the light. We have been working on the visible part, essentially green. So this actually triggered us to start exploring the UV side of the spectrum and moving further. Um, Despite you see some uses and market value of these light emitting diodes and laser diodes in various ultraviolet regions, I would like to show you next. Next. So this the utilization of ultraviolet spectrum to address or cater to or remedy such viruses, because there's certain, not entire ultraviolet is valid for killing viruses, but there's certain spectrum of ultraviolet. So that triggered us to work on this thought, and again with some amazing support work, amazing work from my students, postgraduate students, who were able to pull it off. Next, next. Then we kept working on this idea, UV spectrum, and we produced some work. One is shown on your screen right now. Next, next. This is where we explored the laser diode side of the UV light emission, because laser diodes have a narrower spectrum if we compare it with light emitting diodes, and when we talk of killing coronaviruses. So they essentially respond to a very narrow spectrum of the wavelength. The broader parts of the wavelength are somehow damaging to the tissues, humans, and other bodies that we don't want ultraviolet to affect. So that triggered us to work on the laser diode part of how we can utilize laser diode actually for in ultraviolet spectrum. Next. Um, uh, so this certain particular wavelengths by using, for example, LEDs have been used to treat jaundice in not only India but across the world. I've also seen this in local hospitals as well. So there's this UV environment where kids, newborn babies are placed, and they are well placed and treated under particular lighting environment. So this is again the new world that we live in. Next. Further, these LEDs and laser diodes are, we have just seen one example on the health side that we just saw a moment ago for the babies. So skin treatment, the right amount of lighting is actually very important. If we want to relax, we intuitively know that we need, when we need to relax, we need to dim down the lights. But when we need an environment where we need energy, we need to have the right amount of lighting. So warmer lighting means we want to relax. Intuitively we know, but scientifically this is a chart that shows. And cooler lights means we want when we are working, for example, right now when we're talking, when doing some business things, communications, and different kinds of. So we prefer cooler lights in that. Marine life, lighting is affecting marine life in various forms: growth of plants, growth of fish farms, etc., etc. So right amount of lighting actually, uh, right amount of lighting helps right growth, optimal growth of all these species. Next. So lighting is used in modern poultry farms. We just mentioned fish farms. We would see further next. Agriculture. So vertical farming, smart agriculture, and then different terms used for the same thought. So you see, for example, we have these LED strips. Plants do not require the entire strip. Not every plant requires all the spectrum to grow optimally. So certain plants use, for example, lower wavelength, for example, purple peaks. You can see higher peaks, red. So just giving the right amount of wavelength to the plants to help them grow optimally, which is not only energy efficient, but of course saves time and other kind of emissions, for example, carbon dioxide emissions. Excuse me. So which brings me to this part, how LEDs are reducing the carbon dioxide emission and how they are impacting the environment. Next, uh, the energy difference, the energy conservation of LEDs. This actually, I've been looking at this figure for some time now, and this actually inspired us to work on the energy conservation part of LEDs. We can see how LED, which is on the extreme right, saves, for example, 80 watts, at least 80 watts in comparison to the incandescent bulb, which is on the extreme left. So 100 watts, if this incandescent bulb is consuming 100 watts to produce 1600 lumens, so to produce similar amount of light, similar amount of lumens, 1600 lumens, we see that 20 watts are required by the LED. So moving further, this thought led me to, of course, with my exciting team, not possible without them, to work on how we can save energy using solid state lighting in the three most populous countries, not only of the world, but of course, being specific in this region, subcontinental region. So India, Pakistan, and Bangladesh, and this was well received by the international community also. Moving further, um, so lighting, we all know, I think, Moore's law. Anybody who has studied electronics. So this Heights law is actually the Moore's law for LEDs. So it predicts after every 10 years there is a drop of at least 10 factors in terms of the cost of the LEDs and the increase in light output by 20 times. So far the trend shows that this law is being followed, as we know Moore's law. And this guy that you see is the guy to whom this law is uh, related to. So next, LED market skip. So we know how this market is picking up. 3,5 compounds that I just touched upon during when I started this talk. So these are group 3 elements. This is the combination of group 3 elements, group 5 elements, and combining these two, we get light emitting materials. And when we get light emitting semiconductor materials, so now is the time to adopt these materials into devices. So this guy, Welker, was the first guy who discovered this combination. The guys, Kromer, Alfro, these are again Nobel Prize winners, and they came up with the idea of heterostructures that LEDs and laser diodes actually are made up of. So they introduced the world to heterostructures, and then using heterostructures with the 3,5 compounds resulted in LEDs and laser diodes. So this is a spectrum, different combination of different materials result in different kinds of wavelengths. E is equal to HCO lambda, typical Planck's equation, world famous Planck's equation, which relates how wavelength and energy, which relates energy and the wavelength. Moving further, we can skip this if we need to discuss this further. So when we talk of these light emitting devices, wall clock efficiency is the key. Efficiency actually is the mother of all efficiencies when we talk of light emitting diodes. We would like, this is our end goal, to improve the efficiency. So we would like maximum. What it means in simple words is to increase the amount of light with least amount of electrical energy given to the devices. So this is what we typically know. Output should be greater than the input. So this is these are some definitions of these efficiencies. We can skip this for now. So what we want is we want more of these electrons and more of these holes to recombine to produce more light. So the goal is to make such an arrangement so that more and more electrons and more holes can recombine to produce light. Moving further, so not only producing light, the light has to be moved. The light has to find its way out of the device. So this is external quantum efficiency. So not only producing light within the device, there are factors. I think you all would like to, you all would recall refractive index. So we would like to have the right refractive index, which is again not an easy task to get this light, which has just been produced within this light emitting diode or laser diode to get out of this device. So again, challenge number one is to produce enough light. Challenge number two is to take that light out of the device, and this is the end goal actually. While doing so, we come across some challenges. The challenge of efficiency droop. So when we try to improve our device, what happens is the device improves within a certain range, but it deteriorates, which is you can see the red curves, which are practical curves. Black curves are ideal curves. We would like our devices to follow the black path, but what we end up with is these red curves. So moving further, a list of challenges. You fix one, you get troubled by the other. You fix the other, and you are some other factor comes in and it invades your idea. Or whatever way you are trying to fix your efficiency. Moving further, so this kind of modeled behavior actually inspired us to work on our own idea of producing a model, mathematical model to predict the efficiency. Moving further, this is the model that we predicted for two LEDs. Actually, apparently, it looks like all LEDs work in a similar fashion, which they don't. So we have different LEDs that work differently in different parts of the spectrum. So we have blue LED, which is reasonably well adopted in the world. Green is a troublesome LED because of its inherent material problems. So what we did was we proposed a mathematical model where we predicted the efficiency behavior, and again somehow by going through a lot of troubles and rejections, we were able to finally pull it off as well. Further, some numerical parameters that influence the efficiency, non-radiative due to traps, non-radiative due to auxiliary combination, and we will discuss this if need be moving further. As I just mentioned, it looks like all LEDs work in a similar fashion, but if you see this left graph, actually, the green LEDs suffer the most in terms of the efficiency performance. Blue LEDs are reasonable. UV LEDs, since this curve is normalized, so UV LEDs are actually the lowest, the least efficient LEDs yet. The world has picked up the UV spectrum recently because of the corona, this corona COVID-19. But again, a lot to be done. So we were the first. This was actually my PhD work, so I'm just flaunting it because we worked on green LEDs back then. And we were the first in the world to experimentally measure the built-in field of green light emitting diodes. There were many theoretical proposals, but somehow we were the first to carry it off. Next, it was next. What I missed was this green gap, and why this green is important because the blue LEDs show better efficiency, red LEDs again show better efficiency. Where we lag, where the industry still is unable to cope with is green gap, which includes the green wavelength and yellow wavelength. So we just saw a green part. I'll show you the yellow one over here. So we were for some time thinking to work on yellow LEDs, and finally it happened this year, and This guy Sabgat actually has won PhD fellowship in South Korea, fully funded, and this was again his contribution. Next, these are how actually LEDs look. The LEDs that we see, the nicer, more aesthetic LEDs in our mobile phones, but actually under the microscope, if we see these structures. Um, how expensive is this research area? Being one of is not an easy job, I think, but it is further difficult because of the expenses involved. So if you see one of the leading software tools of this business, this research area, so you can figure out the numbers 3 4 5 6 7 तो 2.5 करोड़ का तो सिर्फ ये सॉफ्टवेयर है which at 225 पाकिस्तानी करेंसी माशाल्लाह करेंसी हमारी is piling down nose diving so ये price आपकी बढ़ जाएगी further uh, this is supported by Gki, of course, with the help of Dean APS. Again, a cheaper version of the leading software, but again, not very cheap if we compare to what to our expenses and to our budget. Next, often it is asked why is there no experimental work? So if softwares are this much pricey, so I think the equipment, just equipment, we are not talking about materials, we are not talking about consumables, nothing else. At current Pakistani currency equivalence, it is up. It is above 7 crore right now. So again, a pricey area. So one has to pay some price to do one of things next. And this is, I think the second last slide. So we run this stream, photonics stream, which is now photonics and microelectronics. Carriers, you can see energy, information technology, defense. The revenue the world is generating just by pursuing photonics is showing on the chart on the right side. And you can see the higher the pie size is, the higher the revenue is being generated by countries. Next, and again, since we talk of photonics and light emitting devices, 4 scholarships are offered by GIK to, of course, FES because we are the only faculty in Pakistan, FES, and then we are the only faculty which runs this stream. So 4 dedicated scholarships, which was up to 2019, we had 2 photonics PS scholarships, which are now enhanced to 4 scholarships. Next. So without these exciting people, none of the things that I just said would have made any sense. So big shout out to these guys. They have been the engine of what I've just tried to convey. So this is my the girl on the extreme left is the girl standing with the Nobel laureate that I just saw you that I just show you. Um, Nobel Prize holder for producing efficient blue light emitting diodes. We have 2 gold medalists here. One is with her degree standing with me. I am wearing the gold medal, actually, ironically, and the guy on the top is sharing and receiving the certificate is the other gold medalist. The guy on the top right, that's me actually, but the guy next to me is the guy who recently won US fellowship, no IELTS waived off, GRE waived off, and fully funded US scholarship. And of course, some undergrad students. So we don't really uh, take up or I don't know why undergrads, but the 2 guys which are shown on the top of your screen are undergrads. One is a FES guy. We present our work in SPI conference held in US, San Diego. And similarly, this guy from FWE, he showed initiative and he came and he contributed to this group. So some acknowledgements, some different organizations that I work with in one way or the other next. And thank you everyone for your time, for your attention. That's it. If you have any questions,